All right, let's see some examples finally of volume by cylindrical shells. And so we'll use the same set of instructions for each problem, so I'll write those down now. Find the volume of the solid obtained. Find the volume of the solid obtained by rotating the indicated region, about the given axis, And so this first example, let's say that our region, the region is bound by the curve x equals 3 minus y squared. This is a horizontal parabola because y is squared, and it opens to the left because the y squared is negative. So we've got this parabola, it's bound by that. It's also bound by the vertical line x equals 3, and the horizontal line y equals the square root of 3. And we rotate, let's say we rotate about the x-axis, all right? And we're going to do this using shells. So the first thing we need to do is kind of get an idea of the graph. Now, we can find some intersections here, but it's pretty easy to tell that if x is 3, if I plug in 3 for x, that y has to be 0, okay? So I'm going to set this up, already kind of knowing what the graph looks like here. I know that if x is 3, then y is 0. And so here's our vertical line, x equals 3. We have the horizontal line, y equals the square root of 3. Looks like this. And the parabola, if you plug in the square root of 3 for y, then x is 0. So you get this point here, okay? And so our parabola does this kind of thing. And then it comes back and wraps around this way, but there's no region contained between that part of the curve and these lines. So the region we're looking at rotating about the x-axis is what's bound by the two lines and the curve. So that's this region. Don't be mistaken here and think it's this region. The x and y axis are not boundary lines in this case, right? The horizontal and vertical lines here are. Okay, so that's our region. So to go about this now, we need to draw a mirror image across the x-axis. And so I'll take the same measurement here, mark it down there approximately, and then this right here will be the corner. So I can set up my corner. didn't hit it at all, did I? And then I'll draw the curved part, looks like that maybe. And so now we've got an approximate mirror image. Now it's harder to draw this than you might think, twisting your body and staying out of the way of the camera and all that. So sorry for the poor image. In fact, I don't think I can handle it. I'm not saying it's going to be better, but I'll feel better about it if I try again. Okay, maybe something like that. All right, so now if we want to create a cylindrical shell to kind of see what we're doing here, then I have to slice parallel to my horizontal axis of rotation. So my region is here from 0 up to the square root of 3. I got to slice horizontally somewhere there. So let's say I want to slice right here. So that's going to intersect this curve and this line right there, and that's going to give me the wall of my cylindrical shell, okay? Then what I do is I draw a mirror image of that down here to get the other corresponding wall of my shell, and then I can sort of draw my cylindrical shell like this, okay? So there's one shell that we could use. We would nest them inside each other horizontally to get the solid that we see here. So now I need to label several parts of this. I know the thickness of my wall. I always like to start with the thickness of the wall, which is measured vertically, so that's dy, and that's so important. That dictates everything about this problem. Okay, so make sure you get the thickness of your wall correct. The next thing is the height of my wall is right here. That's how tall the shell is. And then my radius of my shell is from the axis of rotation to the outer edge. And I want to measure into my original region. I don't want to measure into the mirror image of my region, because these curves down here don't correspond to these equations, okay? So now that's my radius there. All right, now what I need to do is I need to figure out my height in terms of y and my radius in terms of y. Now this is going to be different than disc and washers. You'll see the feel for this in a minute. So the height is going to be it's measured horizontally, so I take the right x value minus the left x value. So in this case, the right x value is the constant of 3. And you can see that no matter where I sliced in my region, 3 is always the rightmost x value. Minus the leftmost x value is based on the curve x equals 3 minus y squared. So I could put x here, or I could put 3 minus y squared, right? Those are the same thing. They're equal to each other. But I need it in terms of y, so I'll do 3 minus y squared as my leftmost x. And then if I simplify this, I can distribute my negative. So 3 minus 3 is 0. Negative times negative y squared is positive y squared. So the height of this shell, of all of the shells, if I were to construct any of them, would be y squared. Now the radius is measured perpendicular to that. It's measured vertically. So it's the top y minus the bottom y. The top y is this guy right here. It's literally just y, right? I need it in terms of y, so I don't need to change this y to x. I just use y. It changes. That part there changes. Now my bottom y, no matter where I measure my radius of any shell, the bottom y is always the constant of 0. The top y is the variable. It changes as we run through our different slices. That's another thing different about disc and washers that takes some practice. Make sure you're paying attention to dy or dx. That sort of indicates this for you. Also, the bottom y here is a constant of 0 while the top y is variable, so we have to use the variable y. All right, so we have our radius now as y. So now we're going to set up the integral to represent the volume. So to get the volume of this whole thing, I've got to do 2 times pi times my radius times my height times my thickness dy. I need to add all of those together from y equals, so y is going from 0 to the square root of 3. And then I need to write my radius and height in terms of y, which I've already done. So now we'll run through the integral. So my radius is y, my height is y squared. Very simple. Now I'll kind of speed up and run through the integral here to get an answer, but that integral is all we'd have to set up to do this problem. All right, so the volume of the solid, when we evaluate the integral and we use cylindrical shells, we get 9 pi over 2. Now, if you wanted to do this a different way, you could do it using washers also. You can imagine if you use washer, you'd slice vertically, perpendicular to your axis of rotation. You'd have an outer radius and an inner radius, and you could add all those together, and you'll get the exact same answer. All right? So you should try that and kind of notice the differences between the two. If you were to use washers, your thickness would be dx, by the way. So everything in your integral for that would be in terms of x. And so that's the big difference between disc and washers and cylindrical shells. If you have a hard time setting up a disc or a washer, you might look at shells because it's going to be set up using the opposite variable. All right, let's do another example. I think I've got 4 examples on the slate for this video. All right, so our next one, our region is bound by the line y equals 2x, the line y equals x over 2, and the vertical line x equals 1. And this time we'll rotate about the y-axis. All right? So these are both just lines. This is the same, so this line has a slope of 2 and a y-intercept of 0. This line is the same as 1/2 times x, so it has a slope of 1/2 and a y-intercept of 0. So if you imagine, they both go through the origin. We're rotating about the y-axis, so I'll leave room to rotate about the y-axis. They both go through the origin here, and we want to look at when x is 1. So we're looking at this vertical line here, x equals 1. That's going to be a boundary for our region. Y equals 2x. Well, if I plug in 1 for x, I get y equals 2 for this guy. So this line hits there. So that's our first line. Y equals 2x is this line here. While y equals, this is the same as y equals 1/2 x. If I plug in 1 there, I get y equals 1/2. So this is a half. That's 1. That's 3/2. So it's going to hit right there, approximately. And so we can see then that our region is that guy. That's the region we're looking at. And we're rotating about the y-axis. So now we need to construct our shells. First things first, I need to draw a mirror image, and I'll use my measurements here to help me. So I need to go 1 unit from my axis of rotation over that way. And then this point, mirror image is there, and this point, the mirror image is up here. And then I can draw my lines to the origin and draw my vertical line. And there's our mirror image. So now, again, the idea is I'm using shells, so I need to slice through my region parallel to my vertical axis of rotation. So I pick some spot from 0 to 1 to slice. So maybe I'll say it's right here. And it doesn't matter where I slice, right? The 2x line is always the top, and the 1/2 x line is always the bottom. So I don't have to split this integral up or anything. I can use the same pattern from 0 all the way to 1. So there's the right side wall of my cylinder, my cylindrical shell, and the thickness of that wall is measured horizontally. Let's draw it up here. It's measured horizontally, so I'll call it dx. And then I need the mirror image of that wall over here. Roughly looks like this. And then I can construct my cylindrical shell by putting the top on it and the bottom. Okay, so there's our shell. So that's my shell. I think I erased my 1 and my 1/2. Here's my height, and my radius runs from the axis of rotation over to the original region. Okay? All right, so now we can set up the integral for this. Actually, first, let's write r and h in terms of x so that I can set my integral up a bit easier. So r is going to be, it's measured horizontally, so it's the rightmost x minus the leftmost x. The rightmost x changes depending on where you slice in your curve. And it's, if I want it in terms of x, it's literally just x, right? Yeah, I just want it in terms of x, so I don't need to solve for x here and get y, right? It's just x. Minus my leftmost x, well, my x value here is a constant of 0. So my radius is measured as x. My height is measured vertically, so I take the top y minus the bottom y, and this is when I have to change variables. I have to go from y to x. So here, my top y is this y, which is my y equals 2x. So when I write it in terms of x, it's 2x. Minus my bottom y changes, it's a variable based on this line, which is 1/2 x. Okay? So those are actually like terms, so I can simplify it. 2x minus 1/2 x is 3/2 x. So now I've got my radius and my height, both in terms of x. Let's take a look at the integral to find the volume. So I get 2 pi times r times h times the wall thickness. I add all of those together. I need to find my limits of integration in terms of x, so that's going to go from 0 to 1. X goes from 0 to 1. And then all I need to do now is set up my r and my h, replace those with x expressions. So r is x and h is 3/2 x. And there's the integral. So let's work through that. So this one happens to work out really nicely. We just keep pulling out the coefficients, and all we get for an antiderivative is the x cubed evaluated from 0 to 1. And luckily that turns out to be very simple, giving us a volume of this crazy solid that you can imagine. It'd be like these wings, and then you swing them around to create a three-dimensional solid. And the volume of that thing is just pi. How amazing is that? All right, so that's an example rotating around the y-axis. If you wanted to use disc or washers, this one would be a little bit harder than the last one. You'd have to use washers because it has a hollow center, and your outer radius would change, right? You'd slice perpendicular to your axis of rotation. So from here up, your outer radius would be measured based on this line, and from here down, your outer radius would be measured based on this line. So you'd have to use two integrals and add them together to get this exact same volume using washers. All right, let's see what's next. Okay, so the next guy, the region is bound by the curve y equals x to the fourth. Very similar to x squared. It just grows faster, okay? And then we've got the curve y equals 4 minus 3x squared. So this is a vertical parabola that opens downward and has a y-intercept of 4, just to keep that in mind. And let's rotate about, not the x or the y-axis, but about the vertical line x equals 1. Let's see how this works out. All right, so since we've got two curves here, they're a bit more complex than those straight lines we looked at before, and it's not just one curve either. So we might want to find the intersection of these guys to help us with our graph. So to find the intersection, I've got y is x to the fourth, but I've got also that y is 4 minus 3x squared. So I can set those equal to each other because they both represent y, and then I'll solve for x. So to do this, I'm going to get 0 on the right side. So I got x to the fourth plus 3x squared minus 4 equals 0. And then this guy factors, so that's what I'm going to do since I've got a 0 over here. So to get x to the fourth, I have x squared times x squared. To get a negative 4, I need a positive 1 and a negative 4 and a positive 1, or a positive 2 and a negative 2. But if I want a positive 3 here, then I better use positive 4 times negative 1 to get my negative 4, because positive 4 minus 1 gives me my positive 3. And so if I were to solve this guy, for x, I'd get imaginary numbers. So I can't use imaginary numbers on a two-dimensional real plane. So this guy has to equal 0, which means adding 1 and taking the square root, x is plus or minus 1. Okay? So the x value where these intersect is when x is 1 or when x is negative 1. And in both cases, if I plug 1 in, I can see that y is 1, right, in either curve. If I plug negative 1 in for x, I also see that y is 1. So I've got 2 points of intersection, positive 1, 1, and then negative 1, 1. So that's going to be helpful for us. So let's see what this looks like. All right, so we're rotating around a vertical line, so I need more horizontal space to rotate. So let's put our axis of rotation in the middle. So there's x equals 1. We're rotating about this line. Okay? And I know that my points of intersection happen at negative 1, positive 1. So let's see. Yeah, negative 1, let's say, is over here. So here's 0. And then there's positive 1. So positive 1 on the x-axis. Here's my y-axis, by the way, where x is 0. And then whenever x is -1, y is +1 is my intersection point, so we'll call this 1. So I've got an intersection point there. The two curves intersect. Sorry, I was in too big of a hurry there. I forgot about this parabola has a y-intercept of 4. So I need to go all the way up to 4 to make sure to get that guy. So here's 2, and then there's 1. Okay, so that's 1. So I know that when x is -1, y is +1, the two curves intersect. And whenever x is +1 and y is +1, the two curves intersect. Okay? So the parabola 4 minus 3x squared looks like this. It opens downward, y-intercept of 4. And then y equals x to the 4th has a y-intercept of 0, and then it actually grows like this. And so we get this region here is what we're rotating around the vertical line. So now what we need to do is create a mirror image over here, and that's not as bad as you might think. I need to measure 2 units to the right of my axis of rotation, like this, and then I can draw my mirror image points. This guy, and then this guy up here, and then I'll draw my upside down parabola, and then my sort of right side up quartic function, okay? So now we've got our mirror image. Now we need to construct our shell, and you always want to do that in the initial region, okay? So I'm going to focus over here and then draw mirror images over there. My axis of rotation is vertical, so I need to slice vertically through this region. So I'll pick some spot, maybe here. I'll slice vertically like this. The thickness of that is dx because that wall is horizontally thick. And then I draw the mirror image of that wall over here. So maybe I didn't do such a good job with my mirror image. It doesn't really matter anyway. Still not great, but hopefully you get the idea. There we go. So now you've seen me struggle, probably like you've struggled in drawing some of these too. I know how frustrating that can be. But there's our shell. The wall thickness is dx. Here's our height. And again, I'm doing all my measurements to my original region. So my radius is measured from my axis of rotation, not to the right, but to the left, like this, okay? So now we'll set up the integral for that volume. So we've got 2 pi times the radius. We need to write r and h in terms of x. I forgot to do that. So r is measured horizontally. So I'm going to take r to be the rightmost x minus the leftmost x. And in this case, the rightmost x, no matter where I draw my cylindrical shell, is the constant of 1, minus my leftmost x's variable based on this curve. I know that y is 4 minus 3x squared, but I don't want y, I want x, so I just put x, okay, the variable x. Then the height of this is the top y minus the bottom y. The top y is based on this curve, the 4 minus 3x squared curve, and I need it in terms of x. So I'm going to use 4 minus 3x squared for my top y, minus my bottom y is based on this curve, which is y equals x to the 4th. So you see, I need y values for each of these, but I need them in terms of x, so I had to replace them using the equations, okay? All right, so we can't simplify that, so those are our radius and our height. So now we get 2 pi times the integral of our radius, 1 minus x, times the height, which is 4 minus 3x squared minus x to the 4th, times our thickness, dx. And we need to integrate based on x values. The x values for our region go from -1 to +1, okay? If you want, you could just do from 0 to 1 because this region is perfectly symmetrical, and then you could multiply the whole thing by 2. So you could try that if you want to. I'm going to stick to the basics here because I feel like shells are hard enough already maybe. Okay, so now this integral represents that volume. I'm going to work through the integral. All right. Disclaimer, I did not use a calculator when I did this, so I tried to take my time. Luckily, because 1 and -1 were here, many of the terms canceled. So we got -2/5, we got -2, we got +8, so that's +6, which is 30/5, plus -2/5 is 28/5, times 2 pi is 56/5 pi. So I hope that's the right volume if I didn't make any arithmetic mistakes. Nothing terribly great about the integral, pretty basic. I chose, because I didn't like dealing with all of these negatives, and I didn't like that the two polynomials here were not in descending order, meaning going from the highest degree to the lowest. So what I did to kind of fix that is I factored a -1 out of this, which turned it into x minus 1. So I put the -1 out here with my coefficient and changed this to x minus 1. And I did the same with this. I factored a -1 out of that, and that switched all of these signs to give me positive x to the 4th, positive 3x squared, and -4. And then I multiplied all those together and did the antiderivative and finished the problem. Okay, so there's our volume using cylindrical shells. All right, let's do one last example. And this time, the region will be described in a graph. So we won't have to come up with a graph ourselves. Sorry. Okay, so the region we're looking at this time is going to be, this entire graph takes place in the first quadrant. So just letting you know how you're going to set this up. You're going to set it up going from 0 up to 6, okay? And then here's 3, and then we've got 2, 1, 4, and 5, all right? So the region we're looking at, on the x-axis we go 1, 2, just making sure you understand what you need. And the first curve we're going to look at goes through 0, 0, and 2, 2, which maybe is about right there. And it's basically half of a parabola. So this curve is x equals y squared over 2, okay? And then the curve above that also goes through this point, but it sort of comes out like this. It's concave down and then curves back around and then over like this, okay? So looks something like that. And the equation for this curve is x equals y to the 4th over 4 minus y squared over 2, okay? And so the region we're looking at, of course, is the region bound by those two curves, this region right here. And we want to rotate about the line y equals 3, okay? So now we will draw the mirror image of this region across the line y equals 3. And now this is going to be a little bit harder, right? So be forgiving when you're judging my presentation here. All right, so this first point is 1 unit from our axis of rotation. So it's about right there, okay? And then this point here is 3 units, so it's up here. And then the parabola here, the mirror image looks something like that, maybe. And then the other guy comes out and then wraps back around and looks something like that, okay? So that's a rough idea of what it looks like. Now what we need to do is construct a shell. So our shell is going to slice through the original region parallel to the axis of rotation. So let's say that our shell slices right there, okay? And the thickness of that wall is measured vertically, so it's dy. Then I draw a mirror image of that up here, approximately. Okay, something like this. And then I draw my cylindrical shell, which maybe looks like this. Okay, so there's our shell. We need a radius and a height. The height is measured horizontally, and the radius goes from our axis of rotation to the edge inside our original region. So don't go up, go down. Okay? All right, so let's write expressions for h and r in terms of y. So h is measured horizontally, so it's the right x minus the left x. The right x is based on, sorry, I should, when I draw my h, I didn't follow my own advice here. H should be measured inside the original region. So the rightmost x is based on this curve, which is just x, minus the leftmost x, let's see, sorry, I need my variables all to be in terms of y. Yeah, something wasn't playing out right. I would have had x minus x, right, which is 0. So the rightmost x is based on the bottom curve. In terms of y is 1/2 y squared. I'm just rewriting it as 1/2 y squared. So based on this curve. Minus the leftmost x is based on the other curve. In terms of y, that's 1/4 y to the fourth minus 1/2 y to the second. Okay? So if I simplify that, I get 1/2 y squared plus another 1/2 y squared gives me just y squared. So I have plus y squared, and then I've got negative 1/4 y to the fourth. Okay? So that's my height. My radius is measured vertically, so it's the top y minus the bottom y. And I need to make sure everything's in terms of y. Now my top y is the constant of 3. No matter where I measure, it's at my axis of rotation 3. Minus my bottom y is a variable for both curves, and it's just y. Okay, like we've seen in all the other examples. Now we can set up the integral. So what we're going to do is we'll take the volume of the shell is 2 times pi times the radius, which is 3 minus y, times the height, which is negative 1/4 y to the fourth plus y squared. Add all those together. Sorry, the thickness of the wall is dy. Add all of those together using y values for our limits of integration. And our region goes from 0 to 2. Remember, our region went from 0 to 2 on the y-axis. And now we can evaluate the integral. All right, so working through that integral, I used the same sort of thing I did in the last one. I didn't like the structure of these. I factored out the negative here, and I factored out the negative here. You see that there. The cool thing about that is that just turns into positive 1. So it's like it never happened, except all of these signs changed, which made it easier for me. Another thing you could do is if you don't like this fraction, I didn't like that when I was multiplying. In retrospect, maybe I would have factored out a 1/4 from this and sucked it out here to be part of my coefficient. Then I wouldn't have to deal with the 1/4 and ultimate multiplication. So anyway, when we do all that work and evaluate the integral, we get a volume of 56 pi over 15. So there are 4 solid examples of, sorry for the pun, solid examples of volume by cylindrical shells. I hope it helps. Takes a ton of practice. Be really careful. Set up your wall thickness first and then base everything on that. Draw your radius and height in the region that you started with, not the mirror image. And those are a really good start to volume by cylindrical shells. Good luck.